Hello and welcome in to lesson 3, video number 2 for Precalculus 1. Again, I will usually try to make just one content video, one example video, but this lesson has quite a bit of content, so I wanted to break it into two. In this video, we're going to be talking about the binomial theorem. So it's like, okay, well, why are we going from foiling now all the way out to binomial theorem? The reason, one of the big reasons, and I've been doing this for several years, is kind of to protect you guys from yourself, so to speak. So up until this point, we've done some fractions, we've done some exponents, we've done distribution. And so a big mistake that people will make is you'll get something like x plus y squared. And people are like, oh, yeah, this is my exponent. So this is just x squared plus y squared. So I'm going to get out my big red marker and tell you, no, it is not. That is not how the exponent rules work, right? If you remember in the exponent lesson 2, I kept stressing for a product, for a product, for a product. If this was x times y squared, then we could bring the 2 in. But with the plus sign, it is not. It is not the case because this is really what? This means x plus y times x plus y. That's what the squared means, right? It's that value multiplied by itself how many times. So that's why we go to the binomial theorem now, is to prevent that mistake. Because now that we're going to be doing the binomial theorem, it's like, oh, wait a minute. No, I can't. I know it's not x squared plus y squared, and we'll see why here in a second. So let's assume, let's say I have a plus b to the 0 power. Well, anything to the 0 power is what? It's just 1. If I have a plus b to the first power, that's what? That's just a plus b. I mean, anything to the first power is just itself. If I have a plus b squared, if I was to write this as a plus b times a plus b, what I would end up with is a squared plus 2ab plus b squared. And let's do one more. If I had a plus b to the third power, so I did a plus b times a plus b times a plus b. When I wrote that all out, it would be a to the third plus 3a squared b plus 3ab squared plus b to the third power. And this could go on forever, right? A plus b to the fourth, a plus b to the fifth, etc. But we can notice a few things here. And this will always be the case here. So if I have a plus b to the n power, well, when I had a plus b to the 0 power, how many terms did I have? 1. When I had a plus b to the first power, I had 2 terms. When I had a plus b squared, I had 3 terms, and so forth. So we will always end up with, so there will always be n plus 1 terms. And that takes us back to this part here, right? X plus y squared. Well, I know by the binomial theorem that I'm about to learn, this has to have 3 terms. So it's impossible for this to be x squared plus y squared. And so that will hopefully catch you guys. Before I started talking about this so early in the semester, that mistake would be made over and over and over again, and it was costing you guys a lot of points. So it's like, all right, let me go to the binomial theorem right away and hopefully stop some of that, and it has stopped it. All right, the second thing we can notice about this expansion that we did, let's look here. So I have a to the first and then no a to the second, a to the first, no a to the third, a to the second, a to the first, no a. So what does that say? The exponents for a start at n and decrease by 1. So here, n is 3, so it's a to the third, a to the second, a to the first, a to the 0, which is just 1. That's why it's not there. Let's look at the b's. So for this one, b to the 0, b to the first, b to the 0, b to the first, b to the second, b to the 0, b to the first, b to the second, b to the third. And so it's what? The exponents for b start at 0 and then increase by 1. And then lastly, the general thing we can notice. So let's see here. The sum of the exponents, 2 plus 0 is 2. 1 plus 1 is 2. 0 plus 2 is 2. How about for a plus b to the third? 3 plus 0 is 3. 2 plus 1 is 3. 1 plus 2 is 3. 3 plus 0 is 3. So that means what? The sum of the exponents is going to be n. So we can figure out for the variable pieces what's going to happen. But what about these numbers in front? How do I know that this is 1, 3, and 3 and 1? And how did I know this is 1, 2, and 1? Well, let's for a minute, let's see if I can keep both pages on here. Okay, let me do this. Yeah. So for the coefficients, well, at a plus b to the 0, I just had 1. For a plus b to the first, my coefficients were 1 and 1. For a plus b to the second, it was 1, 2, and 1. For a plus b to the third, it was 1, 3, 3, 1. 1, 3, 3, 1. So do I have any code breakers here that are starting to notice what is happening? So first of all, I have what? I have ones all down the outside of this triangle, right? But what about the numbers inside? The 2 is what? It's the sum of the two numbers above it. The 3 is the sum of the two numbers above it. The 3 is the sum of the two numbers above it. So if that is true, if I had a plus b to the fourth power, I'm going to get what? A 1 on both outside edges, and then add these guys up. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. And we also notice what? It's symmetrical, right? So 1, 3, 3, 1. 1, 4, 6, 4, 1. It's like if I drew a line down the middle, it looks like a mirror image, right? And this thing would go on forever. And this is what is called Pascal's triangle. So not Pasquale, if you guys are big into EDC, he had nothing to do with this. It was a mathematician with the last name Pascal. And that's what this is called, Pascal's triangle. It would just keep going. 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, etc., etc., etc. So this is great when my n is sort of small. But if I had like a plus b to the 30th power, I don't want to generate a triangle that has 30 or 31 rows, right? And so this leads us to the binomial theorem, which first we need what's called the binomial coefficient. So it's how do we figure out all of these numbers in this triangle if I don't have a giant triangle? So we're going to say the following: let n and r be non-negative with r is less than or equal to n. So the binomial coefficient has this notation, and what this is called is n choose r. So it's not a fraction. There's no fraction line in here. Don't put a fraction line in there. You're going to lose points because you're basically telling me, George, I have no idea what I'm doing, so I'm just going to put a line in there. There's no line in there. It's just n over r, and we call this n choose r. And what this means mathematically, and I'll give you more symbols and explain it, is n with an exclamation point, r with an exclamation point, and then the part that everybody always forgets, n minus r with the exclamation point. And what this means and how we say this is n factorial. So when I have this exclamation point, that means factorial. And by definition, what n factorial means is n times n minus 1 times n minus 2, n minus 3, etc., until you get down to 1. So for example, if I have 5 factorial, this means 5 times 4 times 3 times 2 times 1. Special case, if I have 0 factorial, this is equal to 1. You probably have written that in red. Make sure you have that in your notes. When you have 0 factorial, that's equal to 1. If I calculate a couple of binomial coefficients, let's say I have, as an example, let's do 6 choose 2. Whoops. So 6 choose 2 means what? 6 factorial over 2 factorial, and then 6 minus 2 is 4 factorial. So before I calculate this, what if I have 6 choose 4? Well, this is what? 6 factorial over 4 factorial. 6 minus 4 is 2. 2 factorial. These guys are what? These guys are equal to each other. And where does that show up? That shows up back here. Get it in the screen. Pascal's triangle. So 6 choose 2, 6 choose 4. Same value, just on opposite sides of the triangle. So if I was to calculate this, this is what? This is 6 times 5 times 4, 3, 2, 1. Well, what is 4, 3, 2, 1? That is 4 factorial. And it's over this 4 factorial. So these guys cancel out. And then I have 2 factorial, which is 2 times 1. Therefore, 6 times 5 is 30. 2 times 1 is 2, so 15. So that is this value right here. This is 6 choose 2, and 6 choose 4 has the same value just on the other side of the triangle, which is 15. Let me stop and ask you to think about something here a second. Is a binomial coefficient ever going to be negative or a fraction? So think about that. Can a binomial coefficient be negative, or can a binomial coefficient be a fraction? hopefully you're all screaming at the computer, no, it can never be, right? Because every binomial coefficient fits inside of this triangle, and there's no negatives and no fractions up here. So when I add the numbers above them, I'm not going to get a negative or a fraction from that addition. So if you're ever doing a binomial coefficient problem and you get either a negative number or you get a fraction, you know something went wrong because it's impossible. A binomial coefficient is not going to be negative. It's not going to be a fraction. All right, so we got through all of that. What does that lead us to? That leads us to the binomial theorem. And again, we're usually going to use this when the n value is so large that we can't really do Pascal's triangle. And so what the binomial theorem says is that a plus b to the n power is n choose 0, and then use our facts about a to the n choose 1, then we know what, a goes down by 1, b goes up by 1, n choose 2, a to the n minus 2, b squared, etc. This keeps going until we get to the end, which is n choose n, and b to the n power. So the a's are going to keep going down, the b's are going to keep going up, and all of these coefficients, it stays n, and that number keeps increasing by 1 until we reach n. So that's how we can use the binomial theorem if the n value is large. And then lastly, and that's why there was 2 videos here, because you can see there's a fair amount of content. If we want the general term of a binomial expansion, so I have the following. The term that contains a to the r, and this is important because it's dependent on my a value. In the expansion of a plus b to the n power is given by the following formula. N choose n minus r, a to the r, b to the n minus r. Have this on your cheat sheet. Going to show up on tests. So let's look at an example. Let's say we want the term, so find the term with x to the 5th power in the expansion of 2x plus y to the 20th power. All right, so we need to figure out some things here. What's my n? Well, in this case, n is 20. That's this guy here. What's my r? Well, we know that this formula is based on the a term, which is 2x. So I guess I could write that if I want. A is equal to 2x and b is equal to plus y. And so my r is based off of this first term, the x. And because I want x to the 5th, that means that r is equal to 5. So now that I know a and b and n and r, I just plug them into the formula. So n is 20. R is 5. A, which is 2x to the r power, 5. And then b, which is y to the n minus r, so 20 minus 5, 15. You're going to need your calculator here, 2 to the 5th. This is 32, x to the 5th. This is y to the 15th. You'll have to do 20 choose 5, probably on your calculator. And when you multiply this all out, you should get 496,000 128 x to the 5th, y to the 15th. Now, if you're in my class at UNLV taking Precalculus 1, you guys do not get calculators on the exam. So, of course, a problem like this with these big of numbers is not going to be on the exam because you can't do it without a calculator. Your numbers will be much more manageable, so don't panic like, oh my God, how am I going to do 20 choose 5 without a calculator? You're not going to have to. But in this case, on WebAssign, where they randomly pick numbers, they can get pretty big, so you are allowed to use your calculator on the homework, on the in-class assignments, things like that. But in this situation, or on the exams rather, you're not going to be having access to your calculator. So. All right, well, that wraps up video 2, the binomial theorem from lesson 3. So come on back. We will look at a bunch of examples from lesson 3, video 1, and video 2.